if we were to point AB, f of AB on this surface, the partial derivative with respect to x at AB could be found by moving in a direction parallel to the x-axis. The partial derivative of f with respect to y at AB would be that derivative moving in the direction parallel to the y-axis. But we could move in an infinite number of directions from that point AB. Every direction that we move would correspond to a different direction up on the surface, and that would correspond to a different derivative. So what we want to do is take a point on the surface, and we're going to use a unit vector u to identify the direction that we wish to move from that point AB down in the xy plane. Now that vector u corresponds to a path up on the surface, and the directional derivative will be the slope of the tangent line on that curve at the point AB, f of AB. Now notice that that derivative will not be the partial with respect to x of AB or the partial with respect to y of AB, but it will be a combination of those two. So let's start with a point. We'll use the origin to begin with and define a unit vector u that gives us the direction that we want to find the derivative. This unit vector makes an angle theta with the positive x-axis. So that means that the components of this unit vector, the x and the y components, will be cosine of theta, sine of theta, since u has length 1. So now, the directional derivative that we are looking for will be moving in this direction along the surface of f. So we will be finding the direction moving along the line determined by that unit vector u. So start with finding the directional derivative at the point AB. Since we're calculating the derivative along this line, we need to choose another point out here, a distance h from P. So this distance h along that line L will correspond to a point up here. Now if we move a distance h from P naught, which is AB, this length, this horizontal distance, will be h times cosine of theta. This vertical distance will be h times sine of theta. So the coordinates of this point, a distance h from P, will be a plus h cosine of theta and the b plus h sine of theta. So we'll use these 2 points now to calculate the slope of the secant line passing through the points f of AB and f of a plus h cosine theta, b plus h sine theta. We'll use those to find the derivative. So the limit of those secant lines given by this slope as h goes to 0 will be that directional derivative. So it's the directional derivative of f at the point AB in the direction of u. That's important to realize that the direction must be given as a unit vector. Now, as with any of the derivatives that we've used, we prefer not to find derivatives by doing a limit. So we want to find a formula that'll make it easier for us to calculate a directional derivative. So what we're going to do is we want to be able to take this line, L, and represent it with just one variable. So I'm going to parameterize that line L down in the XY plane. Then I'm going to define a new function, G, in terms of that single parameter that'll have the same values as this function F that gives us the surface. So if the function that I come up with, G, has the same values with F, then that means it'll have the same derivative at any given point. So I'm going to start with the point AB and parameterize this line L by using my unit vector U as the components. So U can be written with U1 and U2. And the x coordinate of a point on that line, remember how you parameterize a line segment, will be A plus the parameter S will be my parameter times U1, and that's the direction. So that's just given the x equation for that line segment. The y will be B plus the parameter S times U2. Now I'm using S to emphasize that S is the arc length. So this is that parameter that is the arc length. So as I move a distance S along that line, I will have actually traveled the length, the distance S as well. So this is the parameter representing the arc length. So if I'm calculating the derivative, I need to know the distance along that line so that when I'm taking the change in the two points on that line, I'll know that that's just the distance between the two. So this is my parameterization for points on the line L. Notice if S is 0, I'm at the point AB. And if S is negative, I would actually be a point to the left on the other side. And if S is positive, I would be moving in this direction, the same direction as U. I want to emphasize again, because the directional derivative is a derivative with respect to the length along this line, it's important that the parameter S actually be the arc length. And that only is going to be true if this vector U is a unit vector. Okay, so now we're going to define a function, G. So G of S, so S is the distance we're moving along that line L, will be the function value F at A plus SU1 and B plus SU2. So we're just evaluating points on that line L at F and assigning those values to the function G. So the function G will have the same values as the functions on that surface. So that means then that G prime of S will be the derivative of F if we're at a point on that line. Okay, well that also means then that G prime at 0 will be a directional derivative of F at AB, because when G is 0, when the point is 0, S is 0, we will be at the point AB. So when S is 0, we're at the point AB. So G prime of 0 will be that directional derivative at the point AB. Okay, so now let's figure out what that G prime or the directional derivative of F will look like. So let's do our tree diagram. We have our function F, and we know F is a function of both X and Y. But X and Y are both functions of S. Okay. So if we wanted to find the derivative of F at AB, we would have the partial of F with respect to X times the partial of X with respect to S plus the partial of F with respect to Y times the partial of Y with respect to S. So that's the partial derivative. That's the derivative of F at some point, and I'm just going to do it at AB. Now notice that actually these didn't need to be partial derivatives. This is just the derivative of X at S. And this is just the derivative of Y at S, since there's only one variable. But what's the derivative of X at S? You come over here, take the derivative of X with respect to the variable S, you'll get U1. Now this partial of F with respect to X could be written as the partial with respect to X, and since I'm just using a specific point over here, that'll be at AB. And the partial of F with respect to Y, I can write as the partial of F with respect to Y at AB, since I am evaluating the derivative at the point AB. And then the partial of, or the derivative of Y with respect to S will just be U1. Now this is G prime of 0, which is that directional derivative at AB. So what we have then is a formula for a directional derivative at a point. Now notice that the derivative at AB in a direction of U is actually a weighted average between, of the partial with respect to X and the partial with respect to Y, where these weights, U1 and U2, are just those components of that vector U. Now, there's another way that we can write this. Instead of saying the partial of partial with respect to X of AB times U1 plus the partial of Y with respect to AB times U2, we could think of this as a dot product. So the directional derivative at AB is the dot product of two vectors, the partial of F with respect to X at AB, the partial of F with respect to Y at AB, so that's one vector, times the vector U1, U2, which is the vector U. So this is going to be the simplest way for us to actually calculate the directional derivative, is by finding the partial derivatives at that point and then taking the dot product of that with the unit vector that gives us the direction that we're trying to find the directional derivative. So now let's apply this. Here's the formula we'll use for directional derivative. Now this is just the partial derivatives in the X and the Y direction. And this is the vector that gives us the direction that we want to get the derivative in terms of. Okay, so now this is the surface that we want to find the directional derivative of, and the point 32 is where we want to find that derivative. So I'm going to use first the direction u. So this is my u1 and my u2. Verify that it is a unit vector. If you take the magnitude of this vector, it would be the square root of 1 over the square root of 2 squared plus 1 over the square root of 2 squared, and that does have length 1. So the magnitude of u is 1, so it is a unit vector. So let's go ahead and find the partial derivatives of this function f. Now I'm going to rewrite this as 1/4 x squared plus 2/4 y squared, so 1/2 y squared plus 2. So the derivative of f with respect to x will be 1/2 times x and then plus 0. The partial derivative of f with respect to y will be 1/2 times 2 times y. So it'll just be y. So if I want the partial derivative of f at the point 32, it will simply be 3/2. The partial derivative of f with respect to y at the point 32 will be 2. So now the directional derivative in the direction of u at the point 32 will be the dot product of 3/2 2 dotted with the vector u. Which is 3 over 2 times the square root of 2 plus 2 over the square root of 2. Common denominator would be 2 times the square root of 2. So this would be 3 plus 4 over 2 times the square root of 2. So I'm just multiplying this by 2 over 2 to get the common denominator. And so that gives me 7 over 2 times the square root of 2, which is approximately 2.47 or 2.5. So now let's find the directional derivative at 3, 2 in the direction of v. So we'll still have our 3/2 and our 2. Now check to make sure this actually has magnitude 1. The first component squared is 1/4. The second component squared is 3/4. So the square root of 1 is 1. So the magnitude of v is 1. That's going to give me 3/4 minus the square root of 3, which is approximately negative 0.98, so almost negative 1. Okay, so now let's see what that looks like. If you were to graph the surfaces, the surface here is going to be a paraboloid. The directional derivative that we found, moving in the direction of 1 over the square root of 2, 1 over the square root of 2, that would be moving at a 45-degree angle from the positive x-axis. If you took the curve that would be the trace up here on the surface, what we're finding is we're finding the derivative at the point corresponding to 3, 2. Here's the point up here, 3, 2, 25/4. We're finding the derivative of the curve, which is the slope of this tangent line. Now, moving in this direction, we will be moving upward along the curve. So as you're moving from here to here, you would actually be moving from this point corresponding to 3, 2 upward on the curve. which means we're moving upward, so the z-value is increasing, and it's actually moving upward at this rate. So for every 2.5 units increase in the z-values, well, for every unit that we're moving along the u vector, we're moving 2.5 units along the surface in the upward direction. So the slope, that's the change in the z-values with respect to that distance along that unit vector u. In this other one, we're now looking at the direction given by 1/2 negative the square root of 3 over 2. So if you graphed that, 1/2 negative square root of 3 over 2, you would be pointing downward into the fourth quadrant. So look at that vector positioned at the point 3, 2. So the point 3, 2 here corresponds to this point on the curve. And as you're moving in this direction given by V along that curve, you would actually be moving in this direction. So you can see the z values actually decreasing. You're going downward, and you're going downward at the rate of negative 0.98. So approximately -1 unit in the z direction downward for each unit that you're moving along this vector v. And so the directional derivative would be negative 0.98. So the z values are decreasing at that point. So as we're moving from here to here. And so that's just the slope of the tangent line at that point.